5.4, mixed practice, sort of putting it all together for permutations, combinations, neither. Either counting or probability. So again, this is like the homework, and I worded them similar to the homework problems. Sometimes I think the homework does word things a little differently, so I'm going to try to point that out here so you can point out, so you can tell which case is it. Is it a permutations case, a combinations case, or neither case? Am I looking for count, or am I looking for probability? Those are sort of the three things that you need to pay attention to. Alright, so the first example. Suppose in your American history class you are assigned to read 6 books from a list of 20 books. How many? So we're looking for the count, not the probability. Can you select 6 out of 20 to read? So you're just going to read 6 books throughout the semester. Does it matter what order you read the books in? No, it just matters that you read them. Right? So order is not important. Order is not important. You're going to read 6 different books, so there is no repeating, right? You can't repeat the same book, otherwise it's not 6 different books. And so this is a combinations example. Combinations. Right? You had 12 books to choose from. You're going to randomly select 6. So how many options are there? So there are a total of 20. Combination, choose 6. So it's a combinations because order doesn't matter. So that's 3, 8, 7, 6, 0 total possibilities. Now this is the total case, right? Total number of ways you can select your book. Next example, how many? So again, count. We're looking for the count, not the probability. How many different ways can 9 people be lined up to buy tickets for a concert? So we have 9 people total. We're going to line up, and lining up is already sort of a term for order, right? It matters how you're lined up. It's different if you're buying tickets for a concert, especially if you select what seat you're going to be in, whether you're the first person in the line or the last person, right? The first person would have more options than the last person. And so line up means order is important. And you're going to line them up. You can't choose, only one person can be first, right? You can't pick the same person to be first twice. You can't pick them to be first and last at the same time. And so no repeats. And so this is a permutations example. Permutations, we had 9 people. We're going to line them up. So there's 9 spots, right? This is the example where I'm choosing all of them. There are 9 people. I'm going to line them up in 9 spots. So there's 2 ways you can do this when you're figuring out the count. You can either do 9 permutation, choose 9, or it's the 9 factorial case, right? Because it's 9 for the first spot, 8 for the second, 7, 6, 5, 4, 3, 2, and then the last spot's just filled out with whoever's left. Alright, so you can either use the permutations key, 9, choose 9, or 9 factorial. Gives you the same answer either way, which there are 3, 6, 2, 8, 8, 0 possible ways to line up 9 people. A lot of ways. Permutations always a lot of ways. How many ways? So again, count. Can we select 3 people? So we're picking 3 people from a group of 9, so we had 9 total, to award them first through third place. Alright, so we had a total of 9 people. We're going to pick 3 of them. We're giving out awards for first, second, and third. Awards always mean order matters, right? It matters if you're first. That's different than if you were picked third, right? First is better than third. So rank, there's a rank to it. Order matters. And so this is a permutation, right? Permutation. And we have to select 3 people, right? So we can't repeat people. If I repeat somebody, I'm no longer selecting 3 different people. So it's a permutation. 9 permutation, choose 3. 9 for, you can do it this way too. 9 for the first reward, 8 for the second, 7 for the third. It gives you the same answer. There are 504 ways I can select 3 people to give out 3 awards if I am picking from a pool of 9 people. Right, 504 is the answer. How many ways can I arrange the 5 letters A, B, C, D, E? Arrange. Order. That's what it means. How many ways can I order them? Order is important. Alright, so I'm ordering 5 letters. I'm 5 letters, and I'm ordering them in 5 spots. So there'd be 5 spots. So this is a 5, choose 5, as if it's a permutations. Because order matters. I'm arranging the 5 letters, so I'm only picking them once. Right? I'm arranging them. So this would be a 5 permutation, choose 5, or 5 factorial, or 5 times 4 times 3 times 2 times 1. Gives you the same answer any way you do it. There's 120 different ways I can arrange 5 letters. Alright, the king has 10 different colored flags that he uses to send code messages to his generals in the field. For example, blue, green, red might mean attack at dawn. Red, green, blue might mean retreat. He sends the message by arranging the 3 flags. There's that word arranging again. Atop the castle, how many coded message can... So, arrange, again, this means order is important, right? If I have blue, green, red, that's different than red, green, blue. Order is very important. It means completely different things. He's ordering. He's got 10 flags to choose from, and he's putting them in groups of 3, right? He's putting 3 flags out at a time, so he's choosing 10 different colors to arrange them 3 different ways, 3 different in our group. And so this is a permutation. Permutation. Order is important, and we're not going to pick the same flag twice. Alright, he's picking out the flags atop the catalyst for his coded message. And so it's 10, permutation, choose 3. So 10 for the first one, 9, 8, comes out to be, there are 720 different messages possible. Next example. Alright, we have a box that contains 8 green marbles, 9 red marbles, 5 blue marbles. We choose 3 marbles from the box at random without looking. This means handful. There is no order. Right? I'm reaching, it's kind of reaching into a bag of candy, and I'm just pulling out 3 at once. I'm reaching into the box and pulling out 3 at once. They were all chosen at the same time. Alright? So that means there is no order. They're all picked at once. There's no first, second, or third. And so this is a combinations example. Alright, combinations for this problem. Alright, we have, just so that we know what's our total number of marbles, we had 8 green, 9 red, 5 blue. So 8 plus 9 plus 5 means there are 22 total. We're going to pick 3. Alright, the first problem, what's the probability? So we're looking for probability this time. Probability is my number in my event divided by my total. I'm actually going to figure out total because we're doing probability in the second part too. So I'm going to kind of do like scratch work over the side and figure out my total. Total outcomes. Well, I had to choose out of 22. That's my total. I had to pick 3. So it's a combination. My total outcomes is a combination 22, choose 3. 22, choose 3. Right, I could pick the combinations 22, choose 3, which is 1540. So 1,540 different ways to pick 3 of the marbles out of this box. Alright, so that's the total. Now we have to figure out the event. The event is that we pick all of the same color. So, meaning all 3 marbles are the same color. And so, I've already figured out my total, so now I'm going to figure out my event. So, write it out in words what it is. I get all the same, didn't say which color. So, I get either all green, or all red, or all blue. So, I pick all 3 are green, or all 3 are red, or all 3 are blue. So combination, if I'm picking 3 greens, well, I had 8 greens to choose from, so this is combination. 8 combination, choose 3. That would be how many ways to get green. Or, so we add, all 3 are red, so red there are 9, so 9 combination, choose 3. That's all the ways to get red. Or, all of them are blue. There are 5 blue, so 5 combination, choose 3 blue, right? So those are my groups. I either get all green, I'm picking 3 green out of 8, combination 3 out of 8, or, so we add because we're using the word or, all 3 are red. I pick 3 from the red, there are 9 reds, so combination 8 from, 3 from 9, red ones, 3 from 9, or all blue. So there are 5 blues, so I'm picking 3 of those. So combination out of the 5 blues, I'm picking 3. That's my event. So my event is, so this is combination 8 choose 3. There are 56 ways to get all green. Plus 9 choose 3. There are 84 ways to get all red. Plus 5 choose 3. There are 10 ways to get all blue, so 150 ways to get one of all color. So my event is 150. All right, now we got to plug it in my probability formula. There's my total. So my probability is 150 ways to get all of the same color divided by my total, which was 1,540. And so there is my probability. So there's the fraction. Again, oh, write the probability as a decimal rounded to 3 decimal places. Alright, so I got to read the problem carefully. So the answer, that's not the answer. Didn't leave myself a whole lot of room to write the answer here. So I take 150 divided by 1,540, round it to 3 decimal places. I'm going to write it below here. So the answer to A comes out to be 0.097. There's the answer to part A. Alright, so the probability that we get all of the same color, either all green, all red, or all blue, is 150 divided by 1,540, the total. And then if I write that as a decimal, it comes out to 0.097. Alright, B now. Alright, so that was A, B. What's the probability? They will be all red. So this is just looking at the one outcome. I actually have the answer all here. Probability, all 3 are red out of my total. Well, all 3 are red was the outcome. Combination, I picked 9 out of 3 reds. Sorry, I picked 3 out of 9 reds out of my total. And so that was 84 out of 1,540. Write it as a decimal rounded to 3 places, 0.055. So the chance of getting all red is 0.055 if I round to 3 decimal places. Alright, so there's a special back in World War II, there was coding, right? Coding was important in order to send messages carefully so that the enemy doesn't get your message. So there was this machine that sent coded messages, right? Because it did an excellent job of coding and decoding. So breaking a code involved finding out, there was mathematics involved, blah, 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 blah. Alright, you can read that. This was actually a problem I took from the web assign. Alright, so to read a encrypted message, it was necessary to determine the initial setting of the 3 rotors, meaning the initial letters. So the letters could be anything in the alphabet, and again, you could repeat, right? Letters like PDX or JJN, right? So they do allow repeats. Alright, so this is only the beginning of the problem for deciphering, so we're just going to look at what are the number of ways we can set up the rotors. What are the number of ways you can set up the 3 letters for each of the rotors, right? So again, we're picking 3 letters, and order matters, but we are allowed repeats. So technically it could be JJJ, right? Repeating all 3, or 2 like we have the J here. This means we're allowing repeats. This is the neither case. It is neither a combination nor a permutation. So we want to figure out, well, how many ways can they set up 3 rotors? That means how many ways can you pick 3 letters, allowing for repeats? Well, we have the first letter and the second letter and the third letter. There are a total number of 26 letters in the alphabet, so there are 26 choices for the first rotor And there are still 26 for the second because we allow repeats, and there's 26 for the third. Since we allow repeats, this is not a combination. This is not a permutation. This is the and where we multiply the same thing every time. So 26 for the first, and 26 for the second, and 26 for the third. So 26 times 26, 26 are 26 cubed, which comes out to be 17,576 different ways to set up the 3 initial rotors, which again is the first part of breaking the code. And I picked that one because, again, there was a lot of things going on in the problem, so just trying to understand what that problem was. So basically that problem was recognizing that you're allowed repeats. So you can pick any letter for the first rotor, any letter for the second, and any letter for the third. So all of them could be 26 of the letters. So 26 for the first, 26 for the second, 26 for the third. So not a permutations, not a combinations. Alright, this again similar to what's in the book, because again I think they word things just a little weird, and so I want to make sure you understand which case it is. Alright, so on Halloween, a man presents a child with a bowl containing 7 different pieces of candy, 6 different pieces of gum. So we're assuming candy is different than gum. He tells her that she may have 4 of each. How many choices does he have? So 4 of each, and how many? So we're counting, not probability. Of each, meaning she can pick 4 candies and 4 pieces of gum, because he distinguished between the 2 different kinds. So 4 candies and 4 pieces of gum. Now, if you're reaching it, so this is the handful case, right? It's a bowl containing, so this is the handful. All right, the kid's going to reach into the bowl with 7 different pieces of candy and reach into a bowl with six different pieces of gum. And so this is the combinations case. It doesn't matter what order you get the candies, you're going to get 4 pieces of candy. It doesn't matter what order you get your pieces of gum, because you get 4 pieces of gum no matter what order. So handful means order is not important. And you're going to get 6 different, so that different means I'm not picking the same one twice. No repeats. So this is a combinations. Alright, combinations. So combinations, I'm picking 4 candies out of 7 total, and picking 4 pieces of gum out of 6 total pieces of gum. So combination 7, choose 4 for the candies, and so we multiply 6, choose 4. Combination 6, choose 4. So it's combination 7, choose 4. That's how many candies that she can get. And so we multiply 6, choose 4 is how many pieces of gum she can get. Alright, so 7, choose 4 is 35 times 6, choose 4 is 15. So we take 35 times 15. There's a grand total of 525 different ways she can pick 4 different pieces of candy out of 7 and 4 different pieces of gum out of 6. The second example, again, you have to read the problem very carefully. He's going to pick, allow the child to pick out of his bowl containing 6 different pieces of candy. So this one only has candy. There's no gum. He tells her she may have 3 pieces. So again, picking out of a bowl means she's selecting a handful. A handful, which means combinations, because order cannot be determined. You're reaching in, you're just grabbing 3 at random. There's no first, you're not pulling out 1 at a time. You're reaching in and grabbing them at random, and so it's the combination case. So combination, we're picking 3 out of 6 candies. So combination 6, combination choose 3. Again, it's a combination because it's a handful. 6 were in the bowl. She reaches in and grabs 3 at one time. There are 20 ways she can do that. Alright, committee. As soon as we see the word committee. Combinations. Committee, combination. The order of selection is irrelevant when we're dealing with a committee, so it's a combinations. Alright, what is the total number of committees? So this is my total in my group. So we want a committee of 5. So that's how many we're picking. So R is 5. We're choosing 5. How many people do we have to choose from? So what's N? So we're picking members from a group of 5 women and 6 men. So there's a total number of 5 plus 6. So 11 total people. So it's a combination. I'm choosing 5 out of 11 people. So 11, combination, choose 5, meaning there is a grand total 462 groups, committees, different committees. How many? So again, not a probability, just a count. How many committees can we make consisting of 2 women and 3? So I'm looking for a specific group that contains exactly 2 women and 3 men. So it means I want to pick 2 women and 3 men. Alright, it's a combination case. For the women, I'm picking 2 women from a total of 5 women. And then, so we're going to multiply, I'm picking 3 men from a total of 6. So it's combination 5, combination choose 2, that's the women part. And, so we multiply, 6 combination choose 3, that's the men part. So choosing 2 women out of 5, combination, choosing 3 men out of 6, combination. Alright, so you fill that out. This is 10 times 20. We'll multiply because it's and. So there's a grand total of 200 ways we can pick a committee with exactly 2 women and 3 men. Alright, the last one. How many committees, so again, count, can we make if Jack is set as the committee chair? Assume that only one member has that name. Alright, so we're going to pick Jack and then finish the committee with the remaining people. Alright, if we've picked Jack, then so again, there's 2 parts to this. I pick Jack and I place him as chair. There's only one Jack, so there's only one way to do it. So we've done this. We've picked Jack. What's left for us to figure out is once I've picked Jack, I then have to complete my committee with everybody else. And since I've picked Jack, there's only 4 people left, or 4 places left on my committee to fill with however many people there are left without Jack. So again, this leaves 4 places on the committee. It's still a combination because those 4 places have no rank to them, to fill with everybody else who's not Jack. So if there were 11 people total, that means I pulled Jack out. There should be 10 left that are not Jack, because there's only one Jack. So it's a combination. So the problem now is just I fill out the rest of my committee. There's now just a committee of 4 that I've got 10 people left to finish. So it's a combinations. N is 10, R is 4. So 10 combination choose 4. So 10 combination choose 4 comes out to be there are 210 groups where we've placed Jack as the chair, we've picked him as the chair, and then finished the committee with the remaining 4 people, choosing from them that are not Jack. So 210. Alright, so that finishes up. And so like I said, the last few examples I picked some from the homework that are very similar to what the homework writes, because sometimes I think the wording is not that great with the homework, and so I wanted to make sure that I did a few examples. So that finishes up permutations and combinations.